we start with some more research topics, and then we walk through some EIP proposal and some discussion on shorter term changes. So the first on the agenda is Maria, who's going to give an update on empirical analysis of historical opcode usage for the multidimensional pricing research we're doing. Yeah.
Hello, hi, thank you. So I'll just share my screen and start right away. Okay. Let me know if you can see these slides, but I'm assuming everyone can. I'm going to give you a quick overview of this analysis we've started to do. This is by no means complete, so there's still some work to do here, but I just want to give you an overview of what we are doing and then some next steps. Okay, so first, what problem are we trying to solve here? As you must be aware, we have very different proposals coming that in some way try to make changes to how the EVM is metering gas. And this can be both updating specific opcodes costs, but also a more long-term research on using a multidimensional metering. And in this context, there's a key question that we need to answer, which is how do these proposals and these changes to how we meter gas and how we decide what is the maximum gas of a block, how this impacts both throughput in terms of transactions, but also the block utilization. And if you want to have more details on what we are doing here, I'm linking below the project proposals, so you can check it out. But a first focus will be on these understanding this question from an empirical perspective. And what does this mean? So, and this is the first part of our approach. Sorry, I was checking the chats if there's any questions. If there are any questions, just let me know. Okay, but so the first part is a more empirical analysis where we are just looking at historical data, and we are checking for blocks on Ethereum, what opcodes were used and their costs, and how the block looks in terms of utilization. And then, and this is more important for the multidimensional metering changes. So a key part here is we have general costs by opcode, but we need to split that costs into its different resources. So for instance, memory, CPU or compute, history growth, state growth, and so on and so forth. And so this involves for each opcode, we need to split that bundle into specific concrete gas costs per resource. And then once we have that, we can simply estimate the difference in gas utilization for different metering regimes. So for instance, using the status code that we have right now, where we just add everything up, or we can make some changes and using, for instance, a multi-dimensional approach where we consider resources in an isolation and limit them independently. Then for part two, so part two is to have a more, the idea is to have a more robust simulation framework where we can test different metering schedules on hypothetical usage of the EVM. So not just looking at historical data, but using, being able to design scenarios. So for instance, say, imagine that we have a certain number of ETH transfers coming in, and then some transactions that are swaps in Uniswap, for instance, and you can design these tests of load on the EVM and see how the block utilization and the throughput would react under different metering regimes. And so the first step is, of course, we need to design these scenarios. We need also to design the block building simulation. So deciding, assuming a certain mempool, how would the block be built? And then how would the maximum limit be defined? And this then enters in the gas metering schedule. And then we can test different gas metering schedules. And here we can be a bit more generic. We can even test things like changing specific opcodes. How does that impact block utilization? So not just doing this separation by resource type, but also changing the costs of opcodes themselves. And for this presentation, I'm just going to focus on part one and show you some initial results on this. Okay, so what have we done so far? So we've been working mostly on collecting and processing these data. So we started with getting a certain range of blocks and then getting all the transactions for each block. And then we are using an RPC call for the debug trace. So essentially for each transaction, it returns what would be the full debug trace, so all the opcodes used and their gas costs. This step takes a long time because for each transaction we are doing an RPC call, and for some transactions they are actually quite large, so they have a lot of opcodes, and they even don't fit in the memory in my PC. So for some of them, I even had to skip them because they were really, really large. And then once we have these raw data, we essentially need to do some processing here to get accurate costs by opcode. And what do I mean by this? So when we get a debug trace, we get something like this. So we have the operation, which is the opcode. We have what is the available gas up until that point. So for instance, here we can see that we started with 62,392, and then this push operation spent 3, and so now we only have less than 3, 3 less than we had before. So we have the 62,389 gas units left. And so we can use this essentially we could use this gas cost column to extract the gas cost per opcode. But then there's a catch for some opcodes. I've noticed that this gas cost is not accurate. So we need to do some calculations on the gas column to actually get the correct cost. And this depends on case by case, so depends on the depth of the operation and the opcode being used. So and this is still something we are cleaning up. So I haven't completely worked out all the cleanup we need to do here. So there's still some mistakes there. And if you ever work with these and or you are interested in working with these, just reach out. I've been looking into this data now for a couple of weeks. So I'm happy to collaborate there and share my code if you want to look into this. And so when we get to this point, we have for a certain number of blocks, we can see for each opcode how much gas was spent. So this is just a sum over all the opcodes, and this is in log scale. So it's actually the differences are a bit bigger, but because we are in log scale, it seems a bit less different. But you can have a sense here of which opcodes use more gas. Yes, Stormy is saying nested call gas accounting is hard. Yeah, I've been feeling that. Yeah, so it's not just a call, but also static call, a delegate call, and then depending on if you enter a new debt or not, the accounting is different. So that's those are kind of the quirks that we need to clean up here. Okay, so once we have this, then the next step is so we already have the overall costs per opcode, but now we need to do a mapping that for each opcode gives us a formula of how to split that among the different resources. And for that, so I shared a message in the channel about this. So I've started to do this in these spreadsheets where some of opcodes were kind of obvious because they only use compute, so you can just assign the entire cost there. But then there are a few that have a multitude of resources, and some of them you even have to do some sort of assumption here. So it's not obvious from the initial documentation which resource accounted for that cost. And so we kind of have to do some guesses here. And for this, I also wanted to do a shout out to Tyler from Off-Chain Labs. He's been also working on these, and he shared some information with me that I use then to complete this table. And I have a first estimation here, but this is not the like end goal source of truth. So this is definitely something that I want to continue to look into and to confirm to see if this is correct and makes sense. But yeah, this was also one of the steps that we had to go through. And finally, once we have the opcode costs and also this mapping that splits for each opcode and their cost, what is the cost by resource, we can apply this mapping and then aggregate by transaction. And what we get at the end is something like this, where we can have for each block, what is the total gas used in that block? And also we can have a split by resource. And you can see here that once we do a split by resource, the as expected, the overall gas usage for each resource it's slightly lower. I should warn that again, I'm still working on some quirks in the data, so there's still some gas here that isn't accounted and assigned, let's say, and so in the end, this doesn't add up completely, but it already gives us a sense of the changes when we go from the current regime to a multidimensional regime. Access is state access rights, exactly. So it's the Merkle reads those is that resource. Yeah, so at the moment I'm not using the memory field because the files were already pretty large. But I'm assuming I'm thinking that I might have to use them to actually isolate the memory expansion costs from the other resources. So it's something that I'll have to look into at some point. But for now, I just made some assumptions on what would be the memory usage by opcode, but that is by no means the most accurate way. Okay, so if you are curious and want to see the code, you can check it here. I'm also happy to explain it, and if someone wants to look into this in more detail, I'm happy to have a chat and collaborate. Another thing I wanted to point out is, so a key part of this is going from the breakdown into opcodes into the total cost, so kind of like reproducing the transaction gas cost. And by doing this exercise is where I found some of the errors that I later corrected, and I'm still seeing that there's some errors that are not completely correct. And for this, essentially, in theory, we could estimate all of these things. So we have the total cost, which we can get from from SHA-2s, which is a data, the data that is provided from the ETH Ops team. We can compute the opcode costs as I was showing you before. And then for the input data costs, we can also get these from SHA-2's canonical execution data. And finally, the gas refund. So this one is a bit harder. So for this, what I did was I had the other 4 components, so I just did the difference between them to get the gas refund. This is where I noticed like some gas refunds were negative, which is not possible. So we are definitely missing some things. And some of them were higher than 20%, which is also not possible because gas refunds have a limit on 1/5 of the total transaction cost. And so this is the point where I've noticed, and this is around, so far in my analysis, like 6% of transactions are showing these weird refunds, and so it's those that I need to clean up. And before I go to next steps, I see we have more message here. Okay, some tooling. Okay, thank you, Joseph. I'll definitely look into that. Then what client I've been, so I think it was Aragon client. Yeah, it was the one from SHA-2. For the traces, it was Aragon, yes. So SHA-2 was for getting the transaction from the block to the transactions, and then the other ones, the other one was Aragon. Then Josem said intrinsic costs. Yeah, so maybe I can check this after, but definitely, yeah, I'll check these tips there on how to fix this. Thank you. Okay, so just for next steps, is the first one is to continue to improve on the gas resource mapping. So a big thing is like trying to isolate the memory expansion costs. So a lot of opcodes would be fairly easy to split if we were able to isolate the memory expansion costs. And so if I have some way using the trace data to isolate these, then a lot of the opcodes would be much more accurate. The second one is like, how do we split the intrinsic costs? So I'm assuming they initially were not just for compute. There must be some other costs that were, so there must be some other logic there to get to that number. So this is an open question to me that I'm not sure. And then also, again, reviewing these splits and see if it makes sense or if I'm missing anything. And then, as I was telling you, the idea of investigating some issues that I found with the single opcodes. So, for instance, one of them was create and create two, that they have some costs that seem to be too low. And I need to kind of investigate why that is happening in some transactions, and then others where the refund, the estimated refund would be much higher than 20%. So it must mean that we are missing some costs. And finally, then once this is all cleared up, I can just run the code and using more blocks as well, and test different resource combinations for metering, and then compute resulting block utilization. Thank you. So if you have any idea on how to tackle these issues I described, please reach out. Yeah, thank you for your attention. If you have also any questions, just let me know.
Hi. Yeah, thanks, Maria. I'm gonna move to next presentation. Yeah, just a reminder that we are targeting like around 7 minutes for a presentation. I know in this one there were a lot of questions in the meantime, so that's okay. I'll also take that into account. Yeah, so next up we have Ivo. Is going to talk about like how we can potentially like take into account prover costs when pricing like some hash functions in particular. Yeah, I think this is very interesting work, like relevant for L1, potentially also for L2 gas pricing. Yeah.
Hi everyone. I hope you can hear me and see my screen. So like essentially what I have been doing or what I have been doing is to like estimate what is the like actual proving cost of the like hash functions in Ethereum. So let's say like on a high level, like what is the issue is that let's say the gas estimates for like different opcodes and precompiles, they're like essentially based on like native execution speed. So like how fast the transactions can be executed like natively on a computer. But if you would to execute the like similar transactions, or if you will try to prove similar transactions like in like CK based systems, then like there is actually like a lot bigger mismatch. And so, for example, particularly for hash functions, and like mostly the issue with the hash functions is that the native execution speed is very fast, but like in CK it is not. And in CK, because like there's the mismatch between like different fields, and there is actually like a lot to do. So the proving overhead there is a lot bigger. So I started my work on I started my work based on EIP 7667. So this is an EIP like essentially like only to, let's say, to modify the gas cost of like hash functions. But like actually like this issue is like it is also like relevant for like different opcodes. So let's say for pairing or let's say elliptic curve precompiles, and also like some other opcodes. I would say like additional motivation like for it is based on like rollups. So it's based on let's say native rollups. So through the execute precompile, and so the execute precompile essentially like what it would introduce is a way like for a rollup to become native. So a rollup can like essentially collect the transactions, like can sequence it as they wish, and then they just post the transactions with the pre-transaction state root and post-transaction state root, and then like L1 can just like verify if this transaction is correct. And then we would have like we can omit like essentially all kind of let's say the L2 overhead. So for the proving or like for running the L2 themselves. So in the current let's say in the current proposal, like essentially like to my understanding is that let's say this execute precompile, it will base, or like its cost would be based on the, let's say, gas usage of the transaction which are verified, and like on a lower level they would actually be proven, and then they would be like separately like verified by like other validators. So like not all the validators would re-execute like all of these native rollup transactions. And like there's also like I would say a benefit for L2s. So L2s can then let's say if the gas cost of the hash functions like it is aligned with the proving cost, then like they can lose the limits on or let's say these arbitrary limits what they have on the number of hash function calls, what can be called inside the transaction. So in addition to like what I have done, so there is a lot of I would say like parallel work. So like the just I would say I think it was yesterday, Connor like released some results about like some other opcodes, and like there is the ETH proofs and so on, and some work is also done by Aclayer. So let's see if there's something in the chat. So what I did is I looked only at the like hash functions, and so I sampled some sample range from Ethereum. So it's like 670 blocks, and I like it's not that much. So it's like about like 2 hours of transactions, but like essentially like the range is small because I wanted to prove like these blocks, and like, it is somewhat time consuming and expensive. But when I traced like all of these blocks and like all of the transactions within the blocks, so what I saw is that like actually the like hash function like usage gas wise like it's not that big. So the biggest usage was for Ketchak. So Ketchak uses like about 0.59% of the total gas in the transactions, and everything else it's basically like I would say a rounding error. Like in my sample, I didn't have like any Blake 2F precompile codes, but when I'm looking at like some more historical data, then there are like some calls, but like not very much. So I was essentially able to identify a single smart contract like which calls the Breakout precompile. I also I ran the SB1 prover on these blocks. So SB1 it is a, let's say, a proving system by Succinct Labs, and like it uses let's say a modification of Red, and yeah, so like essentially like it proves the execution of like of REST execution client, and I run it like using the GPU backend. So like there is a big difference actually, like if you use GPUs and CPUs. And so what I was able to see is that like with SB1, so the average gas proven per millisecond is like 64 gas per millisecond, and like it distributes quite nicely, but there are like some obvious like outliers. I also so my first like hypothesis was that I'm able to like distinguish like what's the proving overhead like for this, let's say, average blocks like from the sample blocks I had, and so like when I measured, then the proving overhead was 0.4%. So like if I would let's say prove the blocks with proving the Ketchup code and without proving Ketchup code, then like with proving with the Ketchup code, so it was like 0.4% slower. So the overhead isn't like very big, but like we have to consider that the Ketchup usage on average was quite small. So instead, I took an like alternative approach. So I ran a local devnet like on my machine, and I'm sorry, on the proving machine, and so I constructed blocks like which are like full of these like hash functions. So I was targeting 30 million gas, and so I want to see like what is the like let's say the prover performance on these let's say edge case blocks. And like when we compare, is that for example for Keccak, when on average, let's say on average block, the proving speed is like 64 gas per millisecond, then like a block full of Keccak is 23, and similarly for SHA-2. For RIPE-MD, like actually, what I saw is that like RIPE-MD, like let's say, it is underpriced in the context of proving performance. But like the issue is that the RIPE-MD like itself, it is like it's very like highly priced. So and RIPE-MD like itself being like quite easy functions what to prove. The biggest issue what I saw was with Blake 2F. So with Blake 2F. So the problem with Blake 2F is like essentially that like I'm able to modify the internal number of rounds inside the precompile or inside the Blake 2F call, and I can like set it up to like arbitrary like high value. So because the let's say the internal round cost it's 1 gas per round, and like when I set it to like 29 million rounds, then essentially I wasn't able to prove I wasn't able to run end-to-end prover. And so I only ran like one small part of the prover, so the core part, and like there I saw that like essentially the overhead is like 20 times. And like based on that, I proposed like some different changes to EIP 7667, like to be more aligned to like what is the actual proving performance. One more issue what I saw was that like for Keccak opcode is that like the dynamic gas cost like it depends on the length of 32-byte words, but like actually let's say internally Keccak works on 136 byte partitions. And so proving wise, like it doesn't make a big difference when like if the input is like 32 bytes, 64 bytes, or like 136 bytes. So the proving cost is the same. So for example, if if you would be to let's say change like how the dynamic cost of Keccak would be computed, then like actually we are able to run or like use Keccak in like more efficient manner. So for example, we can build wider Merkle trees, and this would like instead allow us to do, let's say, less hashing. And like maybe even if we would increase the Keccak gas cost, then the actual number of like Keccak calls will be less, so it will be offset by that. And finally, I also looked at like some like real life transactions like which use the most gas, and like what is the like possible impact on like these transactions. And so, for example, when I was looking at different contracts and different transactions, I can see that, for example, the biggest gas user, like within the sample the range is, for example, Uniswap router. But it doesn't relatively use like that much of gas. So it's still like at 1%. So not particularly. I'm sorry, it doesn't use a lot of gas for hashing. So like even if we would increase the gas cost by 3, like for Kachak, then the impact, relative impact, like wouldn't be that big. And I also looked at different transactions by different senders and so on. So like all of this data like is available at the blog post what I posted on the Telegram channel. And that's it from my presentation. I'll have a look at the questions. So let's see. The first one. I cannot see. Are there like any new questions about my presentation?
Yeah, I can maybe ask a question, Ivo. Like, I remember in the group chat there was a discussion around the fact that the repricing proposal from Jacek will already take care of like some of the adjustment of cost. Like, yeah, do you think that like we should edit that, or like that would be sufficient, or this is like something else that like can be entirely proposed?
So I had to look at the EFP. So like essentially like to my understanding, for example for Kachak, it was that let's say the Kachak let's say static and dynamic cost will be essentially the same, but let's say the base, let's say a cost of or let's say the base cost of one gas, like it will be decreased like by 3. So like essentially, let's say the relative cost of like Kachak against like other opcodes, like it would increase by 3 times. So it would, I think like it would align or like it aligns a bit. But like another issue was that like it also like decreased the relative cost of RipeMD, for example. So like it could make RipeMD, let's say. RipeMD more expensive to prove, because like right now the like RipeMD precompile, it is let's say it is like it's not objectively priced right now. So it would help for Kachak and SHA-2, but not for RipeMD and Blake 2.
Got it. And I think there is a question from Gary. Then we can go to the next, if you have like any comment on that in the chat.
Let's see. Get it. So yeah, so it like so right now it is so that it is like a layer 2 concern, but like there is still I would say like there is a discussion of like snarkifying like L1, and then like if that will be the goal, or like let's say long-term target, then let's say aligning the proving cost with the gas cost, like it would be important. And for particularly for the like as I described for the execute precompile. So the execute precompile, like when I was reading the proposal, it was like its gas cost what would be based on the, let's say, gas usage of the transaction itself. So like then it means that the proving cost and the gas cost would need to be aligned. And yes, the L2s could have different gas schedule, but like it would make let's say from Lina's point of view. So what we are trying to achieve, like we try to achieve like let's say a full compatibility with like EVM specification. So let's say for example if we would have like some different pricing for gas, so it would make, let's say, the developer experience or like already somewhat more difficult. So let's say like if we have some implementations like which assume some gas cost, or like which we have like where we have some limits. For example, when we do like the precompile calls, like for the precompile calls, like we can provide like how much gas we provide, or like how much gas is provided like to the static call. But like in that case, we would need to change that. And like if let's say if some libraries or like if some tooling like doesn't support that natively, then essentially it means that like this tooling needs to take into account some particular like specifics of like different LTUs. But like this is also being discussed. So there is this let's say like rollup geth proposal, which like essentially is to have, let's say, a different execution client, like which is configurable like per LTU.
Got it. Yeah, this is very insightful. Thanks, Ivo. Yeah, if you can unpresent. Yeah. Yeah, so I'll go next. You can see my screen, right?
Yep.
Yeah. So I talk about EIP 7762. I think this is slightly different from like the EVM resource pricing, but like it still falls into like the resource pricing bucket for Ethereum. This is about blobs. And I think, yeah, I'll give like a quick plug overview on this proposal that we are proposing for inclusion in Fusaka. But I think for this group, like this can also show us like essentially when we start to uncoupling these resources and like come up with like pricing mechanisms for like some specific resources, that we need to really understand what like the demand and the consumption for those resources are, right? Like similar to what Ivo presentation from before, right? Like who's really using those like hash opcodes, etc. So yeah, I think that there is kind of like some connection for this group. Hopefully, like this is useful. Yeah. So 7762 essentially does a very small change, which is increases the mean fee per blob. And I'm going to argue that we need this simple change soon. Change is very simple. So like there is one parameter change. So the mean base fee goes from 1 to like still a small number, but like much more in line with what the equilibrium price is. And then there is like two small changes, which is essentially we need to reset the excess blob count when we deploy this change to avoid like a spike. But like this is like a simple reset, basically, as you can see, like a few lines. It's not gonna take too much resources, and I'm gonna argue this is like really needed. So about 2 years ago, like 1 year before EIP 4844 was deployed, I did this analysis. It's a very in-depth analysis on simulating how the market will look in the future. And the main point I discovered is that essentially the price is going to be at 1 at the minimum for a very long time. Like my estimate in this analysis was like 8 to 10 months. And then this is the figure on the left. So like the price is 0 for like many time steps. And then like on the right, the other thing is that whenever we hit the congestion, then like the price is gonna spike exponentially, like and this can cause some instability in the system. So already back then I was proposing like to set a higher minimum price. But this was opposed and like, kind of like really like hard by like some of the core developers. Like they were arguing, oh, it's hard to imagine that blob prices are ever going to be at minimum price because people will start deploying things. But in reality, fees were at 0 for 10 months, and then they are still at 0. It's still problematic. And the reality is that there was a misunderstanding on the demand, right? Like essentially the demand for this blob, the organic demand, only comes from layer 2 chains, which are very inelastic to price, right? And essentially the load had to increase. So like, what is the problem here, right? So there was like this big problem that like when we were like very oversupplied in terms of blobs from like March 24 to November 24, like the price was essentially always at the minimum. And then when we were during this time already, sometimes we were hitting like there was some event like some NFT drop. This was like the ETH inscriptions that then quickly went away. And then there were a few others where like we experienced this problem that like the price takes a very long time to spike up, and for some time there is a flood of blobs and like in the mempool, like I believe like some of the issues identified were like at short-term patches now. But my point is that if you look from November to today, right, like we have been talking about price discovery, etc. But like what is happening is that the fee still often goes to zero, right? And actually it goes to zero like every night. If you look at the bottom left chart, this is like from Monday night. So essentially at night, this is like US time. Sorry, this is UTC time. This goes to zero. And then like every day, like there is this period of like quite a few minutes where like you need to discover price again, essentially. Yeah, so this is not ideal mechanism. And recently, like this is, I'm gonna report some data from the recent AMA, like due to the incidents and due to some other like consideration, like there has been some consensus building that a higher minimum blob fee may be needed. So yeah, this is like excerpt from Vitalik. Ansgar also talked about this, pointing like to some of the proposals. Also, Dankrad, which was initially opposed, it seems that now is actually like in favor of this change, right? Like I think the market has shown us that like the current mechanism is not ideal, and people are realizing this. Oh, oh, sorry. Yeah. Then I want to make like a small plug here. I know this topic is a bit contentious, but like if you look at what happened with its supply since we ship for 844, it's kind of reverse, and we are back to kind of like this supply inflation regime. This is because like essentially like all the burn that was happening before from L2 transaction is not happening anymore. I'm not gonna discuss this in depth today. This is not the main motivation for this change, but like I have like some ideas on why, for the economic sustainability of it, a minimum price makes sense. And this is not for burning more ETH. It's just to make sure that the people that use the network pay for the cost of the network, and not like the holders or other people that are not using the network. So if someone is interested in this, I'm happy to like discuss and follow up. But essentially, to summarize, the proposal is very, very simple. Like today we have this min fee equal 1, which is problematic. The main reason is that there is inefficient price discovery and like some flooding of mempool. There is fee burn. Like I put it in parentheses because like this is not the main motivation, but like there is some concern there as well. And then like this is going to be a sustained problem, right? As we scale blobs like 5x in Pectra, then 5x in Fusaka, and then again, like essentially we're going to hit again the regime where like we are very, very oversupplied, and blobs are not congested. So like congestion pricing like doesn't really work when you don't have congestion. So we can fix it with this simple change. You can think of it as a reserve price, right? Like is a slight improvement of this mechanism. Ideally, like we would like a better mechanism, and there's some ideas that are already being proposed, but this will take a long time to be implemented. These are big changes, right? Like 1559 was like a major change. It took years. So my pitch would be to like, we can fix the current one with this simple change, and then we can have the time to like really like nail down this blob resource pricing mechanism. Yeah. Yeah, if there are no questions, I think Jacek can give an overview of his new proposal. I'll respond to like the other question in the chat. Yeah.
Sure. Give me a second. I find the right screen to show. Okay, can you see it? I hope you do. Right. So to remind quickly, what we do here is that we compared the current gas cost to the actual CPU time that it takes to execute certain opcodes and precompiles. Well, in fact, all opcodes and precompiles. And therefore, by nature, this research focuses on the computational complexity and computational time. So we're not taking into account any network cost, state expansion, storage access, and so on. And we had this number of benchmarks across 7 EVM implementations, and our research has confirmed intuition that many people had, that EVMs are actually getting more optimized, and for many opcodes, it's actually cheaper to calculate stuff. So therefore, there's a room for lowering the cost of it, and also by doing it, we can get a right balance between opcodes and state access cost and memory and so on. We got some feedback on this, and the EAP has been simplified a lot now. Added a lot of explanation why we are doing certain things and so on. But to summary, what we have here, for the most basic opcodes, we plan to change the cost to base, which is 1. So any arithmetic bit operations, it all goes to 1, plus all those strange additional opcodes, and of course all the pushes, dupes, and swaps all goes to 1. Then for the other opcodes, I need to come back to this table here. We said a number of other things to get the right balance between things. A number of other things has to change. For example, the access cost is okay. We have to split it here between warm and cold access cost. The cold access cost is something that we don't touch at all, because that involves getting the data from some kind of a storage on a computer. But warm cost might be treated as computational cost, because it's a data that is already cached in EVM somehow. And indeed, our research confirms that accessing any warm data, that being an account or any storage slot, is much cheaper. I think currently is priced at 100. We propose to change it to 5 gas. Then our research and other research as well has confirmed that the memory access is cheaper than currently costed, and we well, the memory expansion cost, that requires a bit of explanation. So at the moment, it's made of 2 elements. You pay for each word that you expand, and there's a kind of a security guard, which is expansional cost, which prevents from the abuse and overuse. So because that memory is accessing memory is so cheap, what we propose is actually remove the per word cost and leave only exponential security gate. If we go here, we've done some analysis. It's actually not so bad. We can prove that lowering the memory expansion cost doesn't really bring any attack vector on the network. What else? Okay. By changing some or lowering some of the formulas, for example, the access cost and the memory expansion cost, then other opcodes, which we don't change directly, are actually affected by formula changes. So they are going to be lowered as well, especially things like the calls and calls to precompiles, because precompiles are always warm. So calls might become cheaper. We propose to change the three of the precompiles to lower the cost, because that's what our research confirms. What we don't want to change are all the hashing precompiles and Kesak opcode, because as Ivo has showed, we either increase the cost of hashing precompiles, or we decrease everything else, as in our proposal, and then you still have the right balance. There's, I'm not gonna go through all of it, but there's all the explanations that we have in this EIP, so and reasoning for our decisions. So I do recommend reading it to everyone.
Thanks, Jacek. I think, yeah, this is great progress. We should like discuss more in depth now that it is out. I believe there is also the Ethereum Magician forum post attached to this that we can take this discussion to.
Yeah.
I would be curious if there is any points that people have raised that are kind of the most important points of discussion related to this EIP that you want to highlight here.
The hashing precompiles were the main ones, and therefore, after some discussions, we decided to remove them from this EIP, because our research has showed that some of the precompiles might, in this schema, having this new balance, some of the hashing precompiles might be actually benefit from lower cost. But then there are some security concerns and some kind of an abuse concerns of the hashing precompiles. So by leaving them at the current level, cost level, I think we achieved the right balance. And also we are open for any future changes.
Got it. Thanks. So with the last 5 minutes, we have Dano. We can go 2 minutes over since we started. So Dano, if you are ready to present, then you have the floor.
Yeah, if I can get the screen.
Yeah, Jacek, can you unpresent?
Oh, sorry, of course. Yeah.
So what I want to get is a quick temperature check. This isn't a fully fleshed out idea. Well, it is. I mean, the idea is fully fleshed out, but the rationale and legwork hasn't been done for it. But one of the things I think we should consider for memory charging instead of Ethereum is to go away from the current nonlinear format and go for a page costing format. This will simplify the gas schedule for people using it on smaller and make higher memory access within higher index memory access usable, which would increase the general utility of memory for programs. For example, they could use the higher level memory to use a real stack and not have to worry about colliding with things. Everything wouldn't be heap based. So the high level of design would be that the high bits would determine the memory. If we set the page at 32 bits, the lower 32 bits would be the index within a page, and everything above is the page number. The gas schedule would be linear within a page, something like 1 byte per gas. So as you grow within a page, you charge more. And then the nonlinear part comes from the number of pages, and that accommodates the need to do stuff like a binary search to find your page when you have to access memory. To keep it reasonable. Reading will be charged access outside of page 0. Page 0 can be kept special to make sure that reading different page memories doesn't become excessively underpriced. If anything, it'll be overpriced if you use, 1,000 different pages, which I think is fine. We don't want to encourage too many pages. And we would, if you read across page boundaries, you would incur charges for both sides. And if you read across an empty page, you don't create that page. So that's like the high level gist of where I think we should go with the page gas, and that if you use pages beyond page 0, which would represent the entire state of what you can do in Ethereum right now, you'd have nonlinear access charges, but the growth would be linear, and the total size of memory that be kept within a call would be limited by the linear rate to however many gas per byte. So 15 megagas, 15 megabytes of memory is the maximum to be loading, and we punish you if you use an excessive amount of pages gas-wise. So that's something I want to get a temperature check if it's worth pursuing and getting stats on, or if this is too complex and needs a rework.
Charles from Viper here. I've been pretty excited to have, or I'm like looking forward to memory getting like better pricing. I think that the quadratic term, even though it looks nice in terms of like limiting gas usage, or sorry, memory usage, if memory is totally linear, actually, I think that makes it a lot easier to reason about how much memory and how much gas a transaction can use. Because right now, otherwise, you need to like do this whole thing where you simulate recursion in the recursive message calls and stuff like this. So I think it'll be like, I actually did some back of the hand calculations, and if you charge something like 25 to 100 gas per page, an entire transaction can use like 1 to 4 gigabytes of memory, which sounds like a lot, but it's like the entire EVM is how much clients, or sorry, users can use. And that's like a hard limit, and it's based on the gas limit.
Right. I think the current ability of a transaction to use gigabytes depends on the fact that we're underpricing the first few bits of memory that we're accessing and exploiting a flaw in the nonlinear modeling that we start too low.
Yeah. And in other words, like that, I don't really see a problem with having the memory limit for a transaction be like 4 gigabytes. Like it's small for a modern computer, and you just allocate it, and you at the start of, when you start up the node, and you reuse it. There's even a scheme you can use with mmap, where you just like use the upper bits to describe which contract it is, and the lower bits to, represent the page and the memory address. And then you can just like mmap, 2 to the 48 bytes or something, and let the operating system deal with it, I guess.
So the goal isn't to increase memory access across different contracts. It's to, within a single transaction frame, allow page memory.
Yeah, my thing about linear costing is just that it's simpler to reason about.
So we should go for a linear model for everything. I mean,
I think
how do
it's
you
worth
amortize the
sketching
cost?
it out.
Yeah, just sketch it out. Because my concern is when it comes time to look up and do different memory pages, how it's going to be implemented. Clients are not going to have a linear access to large number of pages. They're going to have closer to log level access to getting to more pages. The difficulty grows by log n, so it's not linear when you go to a large number of pages. So that's one concern we need to worry about, is scatter attacks on creating thousands of pages.
Right. I mean, I think thousands of pages. You can also like have a hard cap of like, 1 megabyte per contract or something. And the overhead to keep track of the pages is not very large. Maybe I can do some benchmarks. Would that be helpful?
Right. The proposal I have is to access it as the square root. And the nonlinear is just for growth to discourage it. It's not necessarily tracked to resource usage, and we could fine tune that. Okay, so it might take a few months, but I'll get a more concrete version sketched up once I get access to some memory telemetry from mainnet.
Awesome. Thanks, Dano, and thanks everyone for joining and presenting. We are wrapping up now. Let's continue in the chat as usual until next time. Thank you.